Okay, we're going to continue on here with kinetics. So last time we talked about figuring out the orders of reactions. We also figured out how to find the value of the rate constant. And remember, that is pretty much going to be a sort of table situation where you are given a lot of experimental sort of values. And you're going to use sort of the mathematical approach like we did there of our rate 2 over rate 1 equals our k, a to the x, and b to the y. And as we did in a number of those examples, the goal here is to basically figure out two entries where we really do sort of keep one of the guys constant while we vary the other. That again gives us sort of not as many unknowns to solve for. And once we solve for the order of the, say, b in this case, we then would perhaps pick two other entries where the other one varies and b stays constant. Remember that the order at which you do this is essentially you do need to kind of get the orders for each individual reactant. You need to get the completed rate law at that point, and then you need to basically solve for the rate constant at the end. So obviously you cannot solve for the rate constant until you get the orders and the completed rate law. When you go to solve for the rate constant, as we talked about, you pretty much can choose any of the entries in the table, and they all should, again, give you the same rate constant as a result. Any questions on any of those things? So remember as well, if you get into a situation where maybe you don't have a nice, pretty number, you know, whatever, maybe 1.93. So you take the natural log of, say, both of these sides. And when you take the natural log again, that does bring the x down. Then you just divide it to the other side. So that is mathematically how you could go back and sort of solve these sort of problems if you need to. I would say probably a lot of times, if it's not sort of an experiment sort of problem, you'll probably get pretty good whole numbers there. You could probably just visually look at it and sort of figure out what the exponent is. When you are choosing to put one of them on top and one of them on the bottom, again, typically if you take the larger rate value up on top, that will give you some more whole numbers. Any questions on any of those things there we talked about? Okay, we're going to then talk about specific types of orders of reaction. And there's a few different types of orders of reaction that we're going to talk about. And for the first type of reaction, it's going to be a first order reaction. And that's the first order reaction overall. And we can achieve that by having really one reactant. And it is to say the first order. And we would have a rate law that looks something like this. It is possible to have perhaps two reactants where one is first order, one is zero order, and that would still give you a first order overall reaction. But in this case, we have just one. If we rearrange the rate law here and solve for the rate constant and just look at the units, one really important thing to remember for first order reactions is this: the units of the rate constant are 1 over seconds, are reciprocal seconds. Now, it's really 1 over a unit of time. It doesn't necessarily have to be seconds. Seconds is really the most common unit that we use. Again, as we might have talked about earlier, when we do experiments, a lot of times we measure things in seconds or how many seconds it takes for the reaction to take place. But just so you know, you could have units of 1 over minutes, 1 over hours, 1 over weeks, 1 over year. So it really is sort of 1 over some unit of time is the typical units that you see for a first order reaction. So why is this important? This is important because a lot of kinetics problems, they will not tell you, like with blinking lights, hey, you're dealing with a first order reaction. You to know by looking at the units that, oh, that is a first order reaction that we're dealing with. So Is there a difference between first order, second order, and stuff like that? There is in terms of how you would solve certain problems. There's specific formulas that go specifically with a first order reaction versus a second order reaction. So it's really important to have that understanding of when I see those units of 1/seconds or 1/time, that we are dealing with a first order reaction. Now, taking sort of the rate expression and the rate law together, we get a integrated rate law for first order reaction, and that is the natural log of A is equal to the natural log of A naught minus KT. A is like the final concentration. A naught is like the initial concentration. K is our rate constant. And T here is actually time, not temperature. So T is time here. There's also a half-life equation, as we'll see here in just a second, but I'll put it up here as well. For a first order equation, our reaction, the half-life is equal to the natural log of 2 divided by the rate constant. The half-life is, as the name implies, the time it takes for half of whatever you started with to basically go away. So every half-life, you lose half of what you have there. And, about 10 half-lives, it's pretty much gone at that point. Now, there are two graphs that are associated with a first order reaction. This is the first graph here that's associated with it, and that is concentration on the Y, time on the X. And as you would expect, we would expect as time goes by here, a decrease in the concentration of A, which is our reactant, because it should decrease. I would say a majority of the time when we're dealing with kinetics, we're not really looking at a graph such as that. We are looking at really a more linear relationship. So you could take the integrated rate law there and you could rearrange it and write it as the natural log of A is equal to minus KT plus the natural log of A naught. And this is written in the form of a straight line, which is Y is equal to mx plus b. That means that on the y-axis here, we are going to graph the natural log of A. And on the x, we are going to have time. And that will actually give you a linear relationship when you go to graph it, and a straight line where the slope of that line is equal to minus k. So that is what we see here. The slope of the line is equal to minus k. By the way, the b is the y-intercept, right? Where the line crosses the y-axis. This will give us a straight line as we see in this picture. By the way, the slope of this line will be a positive number or a negative number. It will be a negative number, yeah? And that's a negative slope that we're looking at in that line. And that negative number for the slope, along with it being equal to negative of the rate constant, will turn our rate constant into a positive number, yeah? So the slope values you get from the graph will be negative. That negative, your rate constant will be a positive number in that case if you get it sort of graphically from the equation or the graph. Any questions on that there? So, yeah. Yes, it does. Yeah. So that's the exponential. Yep. So that's basically, so this equation over here is basically this equation before you go through and take the natural log of everybody. Yeah. Most people will use this version of the equation, but that's basically what that means. Yeah. Other questions? So important information off of this first order that you do need to know. You do need to know the typical units that we associate with the rate constant. You do need to know the integrated rate law. That allows us to figure out how concentration is changing with time. And you do need to know the half-life equation. And you do need to know what these graphs look like. Yes, so those are important things that you do need to know for sure. Any questions on that there? So once again, here we can figure out our slope in this linear relationship. And again, our slope, which is basically the rise over the run, will give us negative k. And once again, we do have a negative value here for the slope, which will give us a positive rate constant. So why don't we try this here? The reaction is 2A goes to B. It's first order in A with a rate constant of 2.8 times 10 to the minus 2. How long, how much time, we'll go with minutes or seconds, will it take for A to decrease from 0.88 to 0.14? So why don't you give it a try, see what you come up with. Okay, let's take a look. So once again, they were nice enough to tell us that it is first order. If they didn't tell us it's first order, we would know it by looking at the units there associated with our rate constant, which tells us it's 1/seconds, which is a first order sort of unit. So we definitely want to use the first order integrated rate law there. That has our sort of time and changes in concentration. So in this particular case, we do have the rate constant given to us, which is 2.8 times 10 to the minus 2 reciprocal seconds. We do have the initial concentration of A, which is 0.88 molar. And we do have the final concentration of A, which is 0.14 molar. We're ready to go into our equation at this point. We have basically the natural log of 0.14. It's equal to the natural log of our initial minus our rate constant times time in this case. Yeah. Any questions on that? Now, there's a couple of things when you're using this equation that you do want to sort of watch out for. And it's not really an issue in this particular problem that we're doing, but you do want to watch out for in this range here that these guys are in the same unit. So sometimes you may have a rate constant that gives it to you maybe in minutes or weeks or days or something like that. And maybe your times in seconds, minutes, something like that. So you do want to always make sure that sort of the time value on the back end here really does agree with each other. Otherwise, you do have to do some type of conversion. So in this case, we don't have to do that since we are solving for time. Personally, I'm going to not drop my calculator, but then I'm going to catch it. I'm going to subtract this to that side, and then I'm going to divide that guy, basically. So that's what I'm going to do mathematically. So I'm going to do a little natural log of 0.14 hit equals, subtract a natural log of 0.88. And if you do that, you'll end up with like a negative 1.838279 is equal to negative 2.8 times 10 to the minus 2 reciprocal seconds times t. We're then gonna, like I said, take this to the other side and divide it. Not only the number, but the negative needs to go to the other side as well. That will then turn us into some positive number, and that will give us a time that's about 66 seconds in this case. Yeah. Any questions on that there? So basically what this says in this particular reaction, in just over a minute, it will lose about 85% of its concentration it started with. Yeah. So 85% of it will be gone in just over a minute in this reaction. Any questions on that there? So that definitely is something that you do want to sort of watch out for are the units here. And as we will talk about here in just a second, a lot of times you may need to use the half-life equation and the integrated rate law together because you're missing some pieces of information to allow you to solve for it. So let's talk a little bit about the half-life as we just did there. The half-life, again, is when the initial concentration basically ends up at half. And for a first order reaction, the half-life is equal to the natural log of 2 over the rate constant. And if you do the natural log of 2 on your calculator, that is the 0.693 that you see there. So it is a very common thing in some kinetics problems. And later on, we'll actually see this again when we talk about nuclear chemistry. But that you sometimes will have to use both of these equations together. So in some problems, you may actually just be given the half-life, and you may be given some of this other information, but you may not be given the rate constant. So it's a very common thing that sometimes you have to use the half-life equation to get the K, and then you could kind of use K in the top equation. So that's a very common sort of problem that you do come across as you do sort of kinetics problems, and also as you do some nuclear chemistry problems later on in the chapter. So why don't you solve the bottom there? What is the half-life of N2O5 if it decomposes with a rate constant of 5.7 times? This particular type problem, it really doesn't tell you what order reaction. Obviously, we only talked about first order, so that's probably the right choice. But once again, you do want to look at the units here. And again, we see the reciprocal seconds, which tells us that it is first order. And that obviously means we do want to use the correct sort of half-life equation. That is the natural log of 2 divided by K, which means in this case, it's going to be the natural log of 2 divided by 5.7 times 10 to the minus 4 reciprocal seconds. And that will get you something like about 1216 seconds, or about 1200 seconds, or about 20 minutes, basically, right? So this particular reaction will take about 20 minutes for half of whatever it started with, basically to decompose. And in this case, it is the units of K, right, that allow us to know the order. Any questions on that there? All right, so let's take a look at another one here. All right, in a second, we'll take a look at another one. Here's just a graph of our half-life. And again, if you ever can't remember the formula for a half-life and you're not too bad at math, you could actually solve for the half-life by using the, and provided you remember this equation, that would be good too. So if you just substitute in there A naught over 2 and solve for T, that will get you the half-life equation on any of these ones here, in case you have trouble or forgot it or something like that. Probably easier to remember. So obviously we see half of what we started with, half of what we started with next, and another half-life. And again, like I said, after, a good amount, 10 half-lives, there's not too much left over. All right, so let's try this here. A reaction is first order with a rate constant 2.9 times 10 to the minus 4 reciprocal seconds at a given temperature conditions. Find the concentration after 865 seconds if we started with 0.022 molar, 25 molar left over. Take a few minutes to see what you come up with. We're looking here for the final concentration of this guy. Did not tell you first order. Once again, we have the rate constant and the units to tell us that it is. So we know we should be using our equation here. We have the rate constant given to us at 2.9 times 10 to the minus 4 reciprocal seconds. We are looking for the sort of final concentration. We do have the time given to us, which is 865 seconds. And we do have the initial concentration, which is 0.0225. So we can put everything in here. That will get us the natural log of A equals our natural log of our initial concentration, which is 0.0225 minus our 2.9 times 10 to the minus 4 reciprocal seconds, and our time, which is 865 seconds. So once again, here in this case, we do want to make sure, and it looks like we are going to be okay, as this is seconds and that's seconds. So again, everything's going to cancel out correctly. will not always be that way. So that's a super common error to make people make. That means we really have everything that we need over here on this side. So we could clean up everything on the right-hand side and see what we get. So we're going to do a little natural log of 0.0225, hit equals, minus, open some parentheses, 2.9 exponent -4 times 865. That's going to give us the natural log of A will equal minus 4.04509-ish. To get rid of the natural log on the left-hand side, we need to take the E of both sides, basically, yeah. So we're going to do a little E of that guy. We're going to E that guy up as well. When we do that, those pretty much just go away on the left-hand side. We end up with A, and where did it go? My calculator, there it is. Ends up with a 0.0175. And it does need molarity, as it is the same unit of concentration as our initial guy there. Question on that? Yeah. Most people's calculators usually have these two buttons. You have not the LG button, unless you own an LG calculator. You got an LOG button that button that has an E to the X or an E to the caret. So on most calculators, you usually has to hit the shift or second button top left of your calculator and then hit that guy, and that's how you would do it in most cases. Yeah. And then yeah, you would put the number in as well. Yeah. You want to make sure you keep the negative, don't get rid of the negative or anything like that. You keep the negative if it's negative. Obviously, if it's positive, you keep the positive. So you got to keep the sign as well. Otherwise, you'll get something different. Yeah. Yeah. Say it one more time. It would technically it would, but mathematically, if you do it, we're basically subtracting the sum of the multiplication of those two guys, basically. Yeah. But technically, it is minus K, so technically it does sort of distribute to both of them. But if you kind of do that part in the bracket first, and then the negative can still stay on the outside, and it'll be okay. Yeah. Other questions? Yeah. All right, so we also want to make sure sometimes, right, that our answer makes sense. So obviously our initial concentration here was 0.0225. This thing has gone for 865 seconds, which means my final concentration should be smaller, right? So again, if you, for some reason, got a larger number, you're definitely going in the wrong direction, and maybe some calculation went wrong for you. So don't forget to kind of look at it to make sure it sort of makes sense. You know, you're not gaining stuff over time. That wouldn't be good. All right. All right, so molecular iodine dissociates at 625 with a first order rate constant of 0.271. What is the half-life of this reaction? Okay, so once again, this is definitely first order because it told you, and also again, we still have the units. So we do want to make sure we use the first order half-life equation, which is this guy here. In this case, we could just plug in our rate constant of 0.271 reciprocal seconds. And when you do that, you will end up with about 2.56 seconds, I believe. Yes. Is that a very fast reaction or slow reaction? Pretty fast. Every like 2 seconds, half of it's gone, right? So you're not going to be there very long, probably, right? So the reaction will be done pretty quickly in that case. Yeah. Any questions on first order? Yeah. Now, there are a couple other orders of reactions we're going to talk about, and you may be wondering, you know, how many different orders are there? To be truthfully honest with you, the most common orders are the ones we're going to be talking about, which is first order, zero order, and second order reactions. If you think logically about it, most chemical reactions that you probably have seen or equations that you've seen. How many reactants are there usually? In a lot of cases. Yeah, there's maybe 2 or 1, right? Occasionally you get 3, right? So if you think about the overall orders of reactions, right? You know, in order to get really high orders overall, you would need probably a lot of reactants kind of happening at once, which is usually not the case. So because we usually will see in most reactions, right, like 1 reactant, maybe 2 reactants, maybe 3 reactants, you know, we really don't end up with a lot of like, you know, 7th order, 8th order reactions and stuff like that, because each of the reactants would have to have pretty high orders individually. So very commonly what we see is kind of first order, 0 order, and second order are very common type of reactions, just based on the logistics of, you know, we kind of only have in a lot of cases 2 things, 1 thing kind of reacting. So the next kind of common one that we do come across is a second order reaction. And a second order reaction is a little bit different than a first order. There's really a couple different ways, I guess, or a few different ways you can kind of get there. You could have 1 reactant like we have in this example that is second order and would give us a rate law of K is equal to A squared. You could also have 2 reactants where they're both first order, and that would also get you a second order overall reaction. So, you know, there's multiple ways you could kind of get there. Doing the same thing here with the rate law and rearranging and solving for K, and just looking at the units, the typical units for a second order reaction, which I think we saw a few of them as we did some of those earlier problems, is 1 over molar seconds. So if you have some type of units where it's 1 over molar seconds, and once again, much like first order, the unit of time there doesn't necessarily have to always be seconds, but it's really like 1 over molar, some type of unit of time. It could be 1 over molar minutes, 1 over molar hours. But once again, most commonly is probably going to be seconds. That's a lot of what we deal with here. So just like a first order reaction, you could tell is first order by 1 over seconds for the units of the rate constant. You could tell that you're dealing with a second order reaction when you see those 1 over molar second units. With that being said, there's also an integrated rate law for second order, which is a little bit different. It is 1 over the final concentration of A is equal to 1 over the initial concentration plus a KT. In addition here, the half-life equation takes into account the initial concentration. So the half-life for a second order reaction is 1 over K, which is the rate constant, over there, the initial concentration of A. So the initial concentration of A is important because it will affect, you know, the half-life. So unlike first order, where the half-life is unaffected by the concentration you're starting with, in a second order reaction, the initial concentration does play effect. So tell me, if the initial concentration gets larger, what happens to the half-life? Does it get larger or smaller? So we could kind of do it by just kind of ignoring that part of it. So let's just say we take 1 over 5 versus 1 over 10, right? We take 1 over 5, that's 0.2, right? And we take 1 over 10, that's like 0.1, right? The faster half-life is the one with the smaller concentration, right? And as the concentration increases, I'm sorry, I said that backwards there. That it would be the faster one there at 0.1 is obviously slower than that. So 0.1, as the concentration increases, so does the half-life we would see here. And it obviously increases as we go that way. So in this case, the initial concentration will have an effect on basically the half-life of the equation. Just like what we did with first order equation, we could rearrange it and write it as 1 over A is equal to KT plus 1 over A naught. And that also would be written in the form of a straight line of Y is equal to MX plus B here. So once again, the typical graph that we see for a second order would have 1 over the concentration of A on the y. On the x will be our time. And it will give us a linear relationship, as we see here, where the slope will equal the rate constant in this case. This line, though, will have what type of slope? Positive or negative? This will be a positive one, which is why in this particular case, the slope is equal to k, not negative k. So it is equal to k. This will again give us a positive value for k. So things just like the first order that you do need to know. Once again, units associated with this order. Integrated rate law, half-life equation, typical graph that is done here for a second order. Any question on any of those there? The last type of reaction we're going to talk about is a zero order reaction. And you could get a zero order reaction also in a couple of different ways, but we can have one reactant where the order is zero, basically. And when anything is taken to the zero power, as we talked about, that means it equals 1. So if we solve for the rate constant here, the rate constant for a zero order reaction will basically have the same units that we see for the rate, which is molarity over seconds. So we have 3 different orders of reactions. We have a first order reaction. We could recognize it by the units of K, which is 1 over seconds. We have a second order reaction, which we can recognize from the units of K, which is 1 over molar seconds. And we have a zero order reaction that we could recognize as units of K that are molarity over seconds. So those are 3 really important things to keep straight to help you really choose sort of the right equation as you go after it. We have an integrated rate law, which looks very much like the first order, except there's no natural logging happening here. So this is just the concentration. Final concentration is equal to the initial concentration minus KT. It also has a half-life here of the initial concentration over 2K. So once again, much like the second order, the initial concentration here will play a role in how fast or slow the half-life will be. And like the other equations, we could rearrange this equation and write it in the form of a straight line. And it would look something like this, not like that, like this. There we go. And we would end up with our y is equal to mx plus b here. So once again, for this graph, it will be the concentration on the y, on the x will be time. Once again, it will give us a linear relationship and a slope that is negative. And the slope of this line will equal minus the k. Once again, the 2 negatives there is going to turn our rate constant into a positive value, which is what we're looking for. This graph should look familiar because we've seen this same graph where we concentrated our graph concentration of A versus time for first order. But in a first order reaction, was it a straight line? It was not. It was that line that was decreasing with time. So if you see this guy and this guy graphed and it looks like concentration decreasing with time, that's first order. But if you graph the same thing and you get a linear relationship, it's going to be a zero order. So sometimes that sort of non-linear relationship graph pops up. You got to remember that's actually first order what you're looking at in that one. Again, if you get a linear relationship, it will be zero order here. Just like the other ones here, the things that you do need to know, obviously, is our units associated with K, our time and concentration sort of law there, our half-life, and again, our graph in this case here. Any questions on any of that there? Yeah. It would look just like the rate, basically, because anything to the zero order would be basically equal to the rate. So however, whatever the rate of that reaction would be is basically, you know, how that guy's change rate's the same, basically. The rate expression is basically this here. So they are the same in this sense, except that there will be changes in concentration, changes in time. It just means that basically the rate constant and all that will basically, the rate will equal the rate constant. So they'll be basically the same for a zero order. And a first order, it will be a little bit different. They won't equal each other. So there'll be some differences that will happen there. So it's not like in a reaction, there's nothing happening in a zero order reaction. It's just the relationship of how the concentration is changing over time. And the rate is basically going to be the same. So it's kind of like everybody's changing the same throughout that reaction because they're zero order. Other question? If you remember when we were doing the rate expression, right, we did somewhere some of the reactants were changing more than other reactants, right? So kind of in a zero order situation, you know, basically how everybody's average rate is changing is the same as basically that guy's rate is how it's going to be changing. Other questions? All right, so let's try one here. This is second order in Q. If the initial concentration of Q is 0.01, after 5 times 10 to the 2 seconds, the concentration of Q is 0.001. What is the rate constant in this case? Okay, so this is a second order reaction. So we're going to definitely want to use our time and concentration equation for second order. 1 over A equals 1 over A naught. Remember that this one is actually plus, not minus. So this is plus KT. In this particular case here, we do have our initial concentration of 0.01. We do have the time, which is 5 times 10 to the 2 seconds. We do have our final concentration, which is 0.001. And we are looking for K in this case. So plugging this stuff in, we will end up with here 1 over 0.001 is equal to 1 over 0.01. Plus K, which is what we're looking at, and our 5 times 10 to the 2 seconds. So mathematically, in this case, I'm going to take this and subtract it to the other side. So we're going to do a 1 divided by 0.001. We're then going to subtract it from 1 divided by 0.01. And that looks like we end up actually with like 900 on this side. Is equal to K 5 times 10 to the 2 seconds. We're then going to divide that to the other side, and we'll divide it, and we'll end up with a 1.8 in terms of our K. Now, in terms of units here, technically this is 1 over molarity at this point. When I divide the seconds to the other side, they stay on the bottom. And we end up with 1 over molar seconds in this case. Yeah. Any questions on that one there? Yeah. Yeah. Mhm. Yeah. So it's showing really the linear relationship when you take basically the natural log of it. So you won't get a linear relationship looking at just the concentration versus time for a first order. You'll get that exponential on one. You will get a linear relationship when you do concentration versus time if it is a zero order. So that's the difference between the two. Yeah. Yep. Other questions? I will say that probably 9 times out of 10, if you're sort of presented a graph, that's, and they're like, hey, you know, what is the order, based on looking at the graph, it probably will be for first order the natural log versus the time one. That's usually the most common one, but occasionally the other one does kind of pop into there. So, and people are quick to go just look at the units rather than looking at what's actually being graphed, and just look at the units. People are quick to go, oh, it's zero order because that's like, concentration versus time. But so that's why you want to make sure on that particular one that, you actually look at what is the graph actually looks like in that particular one. Other questions? Okay, so you do need to know, obviously, these formulas and the half-life formulas, and also the graphs. Yes. Obviously, on an exam and quiz, you probably won't be asked to graph, but your graph may be provided for you, where you might have to recognize it. Yeah. So it's a nice little table that sort of summarizes those things. So, you know, this table pretty much you need to know, as they will not be provided for you. So a reminder that you will not be provided formulas, but you will be provided any type of constants or conversion type values or table type values. But these things you do need to know. And as we were just talking about in terms of the graph, you do need to be aware of being able to recognize those graphs. In a couple experiments, you'll be making a bunch of these graphs. So there's one experiment where you do all these graphs. You make like 20 some point coming up soon. But you do need to be able to recognize them as either a first order graph, second order, or zero order graph. Any questions on any of that stuff? All right, so next thing we're going to talk about is sort of the relationship between energy and the rate of a reaction. And obviously, energy and temperature plays a very important effect on the rate of reaction. As we talked about a little bit earlier on, obviously, when you increase the energy, you typically will increase the rate of the reaction, and obviously vice versa there. If you decrease the temperature, which is essentially like removing energy, you will slow down that reaction. So we usually think of it as like you threw your test tubes in a hot water bath, it will kind of increase it. If you threw your test tubes with ice, it will kind of cool everybody down and slow the reaction down. These are two energy diagrams, which you might be familiar with, maybe from previous semester. But just a reminder, we are looking at one that's an exothermic reaction and one that is an endothermic reaction. And when we talk about an exothermic reaction, that means heat and energy is what? Is released, yeah? So heat and energy is released. And in an endothermic reaction, heat and energy is absorbed, right? By the way, one way that we commonly sort of refer to energy or look at energy reaction is our friend delta H. Yes, that is the change in enthalpy. Yeah. And when it's an exothermic reaction, the delta H value is positive or negative? Got quiet all of a sudden. I don't know. That's like a 50-50 shot at that, right? That is a negative value, by the way, for an exothermic reaction. For an endothermic reaction, it should be positive. There you go. That was more people at least on that one. That was like 100% chance, I hope, at that point. So that is a positive value for delta H value. So a lot of times in reactions, right, we're just given the equation at the end of the equation, they'll sometimes go, hey, the delta H is minus 225 kilojoules. Really, the number is not too important in most applications, but the actual sign that you see is sort of important in knowing where's endothermic or exothermic. This is also, we know, is exothermic and endothermic because this is our reactants, right? These are our products. And whenever you look at an energy diagram like this, whenever the reactants are higher in energy than the products, that means energy comes out, yeah? And whenever our reactants here are lower in energy than our products, that means energy is basically put in to do that, right? We've seen energy diagrams before, right? In 50, they teach that. Okay, just want to make sure. It's been a while since I've done 50 here, so all right. So what happens in a chemical reaction, right, is pretty much all the bonds break on the reactant side, and then they kind of reassemble on the product side. And it takes a certain amount of energy to do that. And there's usually a hill that everybody's got to climb to get to their side. And that hill is from where the reactants start to the peak of the hill here. And this is the activation energy. And that is, as it says there, the minimum amount of energy that's required for a reaction to take place. There's really two things that has to happen for a reaction to take place. There has to be a collision, and there has to be the right amount of energy when they hit each other. That gonna hurt. Not all collisions actually result in products being formed. So just because two reactants basically bang into each other, it doesn't mean that you will get products to form. They actually have to hit each other in the right location, kind of the active side of both of them. And they need to have that minimum amount of energy to kind of kick everything off and get the reaction to take place. So not all reactants, when they collide, will form products. And as they go from reactants to products, they are starting to break some bonds. They're starting to make some bonds. So they're breaking and making bonds until they get to the very top of the hill there. And the top of the hill is what is sometimes referred to as a transition state. And that little guy there at the very top of the hill, this guy, that AB with the little symbol next to it, that is what is sometimes referred to as a transition state complex or activated complex. Now, that guy is pretty much at the peak of energy in this reaction, right? Which means, do things like to be in high energy or low energy? Things actually like to be in low energy. So the goal of almost everything that happens is to minimize the amount of energy that happens. Things in really high energy are not very stable. So that's pretty much the peak of energy you can get in this reaction. So usually what happens with this is it will very quickly, a lot of times, kind of drop down to the other side to make products. A lot of times those transition state complexes are super hard to try to isolate because frankly, they go by really quickly. They're like there for a moment. And it's because they're super high in energy because they're kind of breaking bonds. So they got partially broken bonds, partially made bonds. They're kind of like a transition sort of point that's happening in this reaction. We see the same thing over here between where our reactants start and the top of the hill here being our activation energy and our transition state that's occurring there. The activation energy is really important because if I have a large hill for everybody to climb to get to the other side, would I expect that reaction to be fast or slow? Probably slow, right? And that's because there's going to be a much smaller amount of reactants to have enough energy to get up and over the big hill, right, to get to the other side. Than if you had a much smaller hill, right? There would be a greater amount of reactants that can pretty much manage to get up and over to the other side. And that usually would increase the rate of reaction. That's also why which one has the higher activation energy between exothermic and endothermic? Endothermic. Why? You know, he kind of has to put a little extra energy in there to kind of get the thing kind of moving, if you will. It needs to absorb some of that energy to get enough people to get up and over to the other side. If I wanted to calculate the delta H for this reaction, how would I do that from the graph? The delta H is the difference, right, between the products and the reactants, right? Products minus reactants. So it's the difference in the energy, right, between the products and the reactants. That's how you calculate delta H, right? All the delta H's of the products minus all the delta H's of the reactants. And that's because that is a state function, which means the only two things that are important is where you start and where you finish, which in a reaction, where you start is the reactants and where you finish is the products, right? So that's why we always take products minus reactants. Basically the difference of where we start and where we end. We can speed up a reaction, as we'll talk about here, by adding a catalyst is one way that you could speed up a reaction. And a catalyst, as we talked about a little bit earlier, simple as it's like a piece of metal and like everybody's attracted to the metal. So everybody's in the same location at the same time, which means they can start reacting a lot quicker than they would if they were just kind of flying around trying to find one another. But ultimately, what a catalyst does is it pretty much finds that alternative pathway and it lowers the activation energy. So it lowers that hill that the reactants has to climb to get to the other side. And typically, because of that lowering of the activation energy. Any questions on any of that there? So there is a relationship, which is sometimes referred to as the Arrhenius relationship, that deals with temperature, activation energy, and rate constants. And this is one version of it, which we don't use all that much here. We will see it in a second, where we kind of take the natural log of it here, and we will use usually that version. But there's a couple of things here that you should be aware of. The temperature, when we use sort of the Arrhenius equation, does need to be in Kelvin. And hopefully we remember, right, that's a 273 addition on that. The gas constant here is actually the one that involves energy. So it is not the one that you use for the ideal gas law, unless you want to do a lot more. So this is the Arrhenius equation. And like I said, we're going to see really a couple of versions of this equation. There's really one where we kind of specifically use it for graphing. There's one where we kind of use it more of a mathematical approach to it. And I say very rarely we will kind of use it in this version, which I mean, there are kind of the same thing. So the activation energy, as I said, as the reaction is happening, that is the energy barrier that everybody's got to climb to get to the other side. When we reach really that peak of that energy, that is what's again sometimes referred to as that activated complex. It is really happening at that transition state. And we have the really kind of unstable guy, if you will, at the very top, where, you know, he's really in that transition between fully breaking those bonds and now kind of fully making the bonds on the way back down the hill. So here's an example. For example, this is actually just a rearrangement here of this molecule. But what is going to happen is we're going to get these bonds to start to break and reassemble with the carbon actually attaching to the left there. So as this process occurs, again, starting to break those bonds, starting to sort of make those bonds and rearrange as we get to the top, and then again drops down here. So once again, we see this as an exothermic, as our reactants are higher in energy than our products. And once again, that is how we calculate our delta H from the result of that. All right, that's sort of what we've been talking about. So taking this equation here and taking the natural log through it does give us the version of the equation that we really do kind of use a little bit more than the top one there. And we oftentimes will use this version of the equation in a graph type of situation. And that's because this is written in the form basically of a straight line. So when we have our natural log of K is equal to minus E of A over R, 1 over T plus the natural log of A. When we put in our equation for a straight line, that will be y is equal to mx plus b. So once again, this allows us to get a nice linear relationship, and we can use the slope here to basically calculate the activation energy for a reaction. This relationship here on the left is not graphed using this, but it is just graphed basically from there. And what we do see here is as we have a lower temperature, we have a much lower rate constant, which means reaction is going to happen a little bit slower. As the temperature starts to increase, we end up with a much higher rate constant. So again, we see the rate start to increase as the temperature increases. And as I mentioned, that basically means we have a lot more proportion of molecules that will have a sufficient amount of energy to reach the other side. The more common graph that we use can be found from that equation there. That means on the y, we typically will graph the natural log of K. on the X, we would graph 1 over the temperature in Kelvin. And that typically will give us a linear relationship such as this, where the slope is equal to minus E of A over R. Now, R is the gas constant, that 8.314, which means basically if you did the graph, you could get the slope by doing a best fit line and times it by 8.314, and that will give you your activation energy. By the way, the graph that I just drew here on the bottom, positive or negative slope? Negative. With this negative means my activation energy should be always a positive number. And we see that in those graphs that we saw, right? The activation energy was that hill, right? Positive, wasn't going down or anything like that. So activation energy, when you calculate it, should always be a positive sort of number. And if you do calculate it this way, by multiplying basically the activation energy is equal to minus R, bless you, times the slope. What are the units of energy that you will end up with here? You'll end up with joules, not kilojoules. So very commonly, activation energy is given in kilojoules. So you may have to divide it by 1,000 to get to the kilojoules. But when you do it from the graph like this and you multiply by R, you will actually end up in joules, not kilojoules. So that's also something to keep in mind. A lot of times the questions will ask for it in kilojoules and stuff like that. So here is more of a plot that you would use as a straight line. Once again, our y is equal to mx plus b. And you can see you get a nice linear relationship there, where once again, in this particular case, minus E of A over R would give us our activation energy. So a couple of things about those. Some of these things we've talked about. The exponential factor there is basically represents the fraction of molecules that have basically enough energy to get over the activation energy to the other side. The higher the activation energy, again, the lower the proportion of molecules will have to get to the other side. And again, usually will result in that lowering of the rate. Extra energy comes from converting the kinetic energy of motion to potential energy when molecules collide. Increasing the temperature does increase the average kinetic energy, gives everybody a little bit of boost of energy, which means when they do collide, there should be, in a lot of cases, good to go where they might not have been before. Increasing the temperature will give those molecules sufficient energy to get over the activation energy. And obviously, as I think we saw earlier, you know, typically speaking, if you raise the temperature of a reaction, a lot of reactions by just 10 degrees Celsius, you can sort of double the rate of the reaction. And obviously, the vice versa of that would be if you threw everything on ice and really cooled everybody down. If you wanted to kind of slow down the reaction, that would be a way you could do that. It is, yeah. So basically. It's not. Sometimes you do have to calculate. So for example, let's go back here. If we were to do sort of a graphical version of this, and we'll do an example here in this chapter, if I wanted to find A would equal what based on my graph? We would look at the y-intercept, right? So you would get the equation like you did your best fit line, and the y-intercept would equal the natural log of A, which means you could take the E of the other side. Now the units of A oftentimes will end up with the same units as K. So whatever the units of K happen to be for that particular reaction, that is usually what you'll end up with in terms of the units for A when you do it off of a graph. And that's because that is the y-intercept, right? And on the y-intercept, it is the natural log of K, right? To solve this, right, we need to take E of both sides, which basically gets rid of the natural log part and brings it back to K. And that is typically then the units that you would use for the activation or frequency factor. By the way, when you take the natural log of K, no longer has units, yeah, at that point. So it doesn't really have units at that point. But when you do take the E of it coming backwards, the units of K kind of come back. So sometimes people are like, what are the units? So usually that is the case. A will have the same units as whatever the rate constant is. And that's how you would calculate it in most cases, using that formula and a graph. You could mathematically, if you had some of the numbers, plug it in and solve for A into that formula as well. But most of the time, probably graphically is how you would kind of determine that based on the y-intercept. Other questions? So here's a graph that sort of demonstrates that idea of raising the temperature at the second temperature, which is the red line there. There is this much of products, I'm sorry, there's not much molecules that have enough energy to get to the other side. When we look at the lower temperature, which is actually the blue line, it is only up to here in terms of the amount of molecules that have enough energy to get there. So you can see by raising that temperature, we gain that much more in terms of molecules that have sufficient energy to basically hop up and over the hill to the other side by raising that temperature. Again, because they have a lot more energy to allow them to do that. All right. So I think this might be a good place to lay it up. I'm looking at what got on. Yeah, so we'll wait and we'll do that example, I think, next time. Any questions on any of that stuff there?